Okay, so since we had a snow day yesterday, we're going to do a quick mini lesson for lesson 7, and then we're going to move on to lesson 8. So if we look at class example number 2, we can look at this equation and we can say, oh, that's not a quadratic equation. All of our a's and a squareds are part of the denominators. So to deal with it, we just go like this. And you multiply everything by a squared. Like this. And so that will give you a squared times 2 over a squared plus a squared 3 over a is equal to negative a squared. And so we can see that, oh, this cancels out really nicely. And we know that a squared is equal to a times a. So one of those a's cancels out. And so this will give us 2 plus 3a is equal to negative a squared. And then we can move it all to one side by adding a squared to both. We'll get a squared plus 3a plus 2 is equal to 0. And then it's just an easy factoring problem. So we can go like a plus 2 multiplied by a plus 1. And so we know our roots are negative 2 and negative 1. So let's see if we can erase. So if you move down to the second part of the page, you can see that we have our quadratic equation. So we're just going to set these up like we did on Tuesday. So we have a is equal to 1, b is equal to negative 6, c is equal to 5. And we can put these into our quadratic equation just like we are so good at doing. Okay. So then we know under our radical sign, if we were to solve all of this, we'd get 16. So we'd get 6 plus 4 over 2 and 6 minus 4 over 2, which would give us 10 over 2 is equal to 5, and 2 over 2 is equal to 1. So we know our roots are 5 and 1, and we can see them right here. Okay. So for the second example, we're going to do the same thing. So we have a is equal to 1, b is equal to negative 6, c is equal to 9, and we can put those into our quadratic equation just like this. And we'll get 36 minus 36, so we'll get 0 under that radical sign, which gives us 6 plus 0 and 6 minus 0. And so 6 over 2, we know that our roots are equal to 3. So if we look at our graph, we can see that right here. The graph just touches the line at 3. So it only touches it at one place. And so if we look at the last one here, we have the same a is equal to 1, b is equal to negative 6, c is equal to 13. Plug this all in. And this time we'll find that under the radical sign we get negative 16. And so we can't take the square root of a negative number here, right? We've known that for years and years. And so we know that there are no roots. And so if we look at the graph, it might look something like this, or like this. It's not going to touch that x-axis at all. So if you flip over, this b squared minus 4ac is called the discriminant. And so this is everything that's under that square root sign, right? And so what the discriminant does is that by solving for this, we can figure out whether we have 2 roots, 0 roots, or only 1 root. So if we look at the problems we just did, we can notice that when we had 2 roots, we had a positive number underneath the radical sign. when we had one root, b squared minus 4ac was equal to 0. And when we had no roots, it was a negative number, so we couldn't finish solving the equation. Okay? So we're going to skip down to here. And this is going to be good study sheet notes. Okay? So when the discriminant is equal to 0, we say that the roots are real and that they're equal. So this is like example 2 where we had both of the roots were equal to 3. If the discriminant is greater than 0, so it's a positive number, we say it's real and unequal. So this is like example 1 where we got the roots were equal to 1 and 5. And if the discriminant is less than 0, then the roots are non-real. Okay, so that just means we can't even solve the problem. There's no answer. So I'll just write when the roots are positive and when they're negative here. Okay, so this is the mini recap of lesson number 7. If you weren't here yesterday, watch it on YouTube because there's a lot of examples and it has the homework on YouTube as well. So, lesson number 8. We'll get this going. Okay, so we'll just open this up. Okay, so let lesson 8 open up. Bless you, Michaela. You get that, YouTubers? Okay. So, lesson number 8, if everyone wants to open up to page 347. Page 347. And so, we've learned a whole lot about quadratic functions, and now we're going to be solving problems with them. So, we're going to start getting into word problems. And so today we're going to learn how to solve them 100% on our calculator. And we'll wait. And tomorrow we'll learn how to solve them algebraically. So today's kind of like the quick, easy methods on the calculator, which is awesome. Yeah, a lot of the stuff that we've done will be things you already know how to do, but it's in a problem, right? So now we're learning how to look at a problem, and if they say like, when does it second last? I don't think it's too bad. Maybe next class. Okay. Okay, so we're going to go right to the first problem. So the height h in meters above the ground of a projectile at any time t in seconds after the launch is defined by this function. Okay, so t is seconds, and then h is height. So they say use a graphing calculator to answer the following. Sketch the relevant part of the parabola on the grid. So they're asking us to basically draw a picture of it. So let's go y1 is equal to negative 4 x squared plus 4 8x plus 3. So we're substituting x in for our t's. Nothing. Okay, so we'll go negative 4 x squared plus 48x plus 3. So you might have a graph where you can't really see anything. So if I go second, or if I go zoom our standard one, you get something that looks like this, right? And this isn't very helpful to us at all. We can't even really see what's going on. So what you would do if your graph is not fitting in our windows, usually the way I start is I'll go second zoom, or not second zoom, sorry, zoom. And if you go down to 0, you can see zoom fit and hit enter there. So some things we have to think about when we look at this, like this is a word problem, right? So we're dealing with height and time. So if our time is our x-axis, do we need any negative x? No. So you can go, okay, Windows, I'd maybe make it like -5 or something, because if we're looking at intercepts, sometimes it's nice to be able to see the intercept. And our negative y, do we need any negative heights? No. So I'll make it -10 or something, and you can hit graph again. Okay. So what would you do next then? Exactly. So what should we maybe change it to? 50? Sounds good. They might ask for your intercepts. Okay. But for the first part, they ask you to draw a picture of it. Yeah. So I changed the x max to 50. And that's honestly just how you get a good picture of your graph, is you kind of like say, oh, I want to see my x-intercepts. Well, let's change it to 50 and see what we see. So there's no real like trick to it. It's just kind of playing around and seeing like, oh, that's good. No, I want to see more of it, or stuff like that. Okay. So, and I'm just going to change this to 175, because I don't like it when my graph comes really close to the top and I can't really see it. Okay. So even if your graph doesn't look exactly like mine, can you get a good picture of it? Okay. So all they do is ask us to draw it. So I would draw something like this, and I'd say my x max is 50. I have my y max is 175. And to sketch it, this is all you have to do. You don't have to like have it perfect. You're not being artists right now or anything like that. And I'd maybe write our x-axis is in seconds, and our y-axis is height in meters, just so we don't forget what we're actually looking at. Okay, so for B, they say find the height of the projectile 3 seconds after the launch. Because that's what I have in my calculator. So I made it 175 centimeters, right, or meters there. So you can have it as 200, you can have it as 150. As long as you can see your graph. Okay. It doesn't have to look exact, but as long as you get a good view of it. Okay. Yeah. So with yours, Andrew, like we're dealing with, yeah, you just have different windows than I. Yeah. Because, so I changed it to -10 because we're talking about something that's being shot into the air, so we don't need any negative y's. Yeah, it's not going to be below the ground. Perfect. So they say find the height of the projectile 3 seconds after the launch. So is our seconds, can someone tell me with their hand up whether we're talking about x's or y's? Kevin? Yeah. So we know that our 3 seconds is our x's. And so on our calculator, we can go second trace value, x is equal to 3. And so we can see, okay, when x is equal to 3, that means 3 seconds. So the height is 111 meters. Yes. So you can also go to table and find it. Yep. So just like when we're finding our y-intercepts, we make x equal to 0. If we were to do this algebraically, we'd say x is equal to 3. Okay, and well, actually, that's what we're doing tomorrow. So sneak peek right there. So, okay, so when we write this, we say h at x is equal to 111. So the answer is 111 meters. 111. Okay? Are we ready? I don't know about that. Okay, so they say the maximum height reached by the projectile. So I'm going to show you how to find maximums on your calculator now. So I need everyone watching and listening. So we go second trace, and you can see, oh look, number 4 is maximum. So you hit enter, and you'll notice it says left bound. So we can see the maximum on our graph is like right here, right? So when it says left bound, we hit enter when our little blinker is to the left of the maximum. And we notice it changes to right bound. So we have to move this to the right of the maximum. And then we hit enter twice. And so we get the maximum is x equal to 6 and y is equal to 147. Yes, Lucas? You could, like, the table works pretty well for this one because we know it's 6. Like, we can see, like, oh, it's going to be close. But if your maximum was at, like, the point, I don't know, 260, you wouldn't want to scroll through and be like, okay, like. So in a graph like this, that's a pretty easy solution. But in some of them, it won't be. Yes? Okay. Yeah. The calculators might just be graphing or rounding differently. Well, you can be wrong. What the heck? Trace 4 there. Enter. Well, then you definitely want the answer the teacher has, right? So you'd be wrong. Okay, so find the maximum height, 147. So you go, okay, max is 147 meters. Yeah. And like you guys were finding like differences in the x values, but for this question with the maximum height, the only one we care about is the y anyways. So the x is kind of, it doesn't matter. Okay? And now for D, they say after how many seconds after the launch is the maximum height reached? So 6 seconds, you got it. Yeah. So we know our maximum is 170 or 147, and it's 6 seconds at that point. Okay? So for number or letter E, we say what is the height of the projectile at the launch? So at how many seconds are we launching it? Okay, can I have someone with their hand up? Yeah, exactly. It's going to be at 0, right? So it's going to be at our y-intercept. So you just go second trace, value 0. And we find that it's 3 meters high. at the start. Okay. And then the last question they have, so we can wait until you guys are ready to go, because ready? Perfect. So the last part for this question is determine when the projectile hits the ground to the nearest tenth of a second. So when we look at this graph, we can say like this is almost what, I don't know, whatever it is, a cannon or something, looks like with its path in the air. So it goes up, and it comes back down, and it's going to hit the ground right there. That's the ground. So we know that the x-intercept is when it hits the ground. So I already have on my calculator y2 is equal to 0. So you can go second trace, intersect, and just remember that we do have another x-intercept here, but it's a negative x, so we don't care about it because it's a negative time. So just make sure that you move your little cursor all the way over to the other one, because this is the one we care about. And you just go enter, enter, enter. And we get that after 12.06 seconds, so 12.06, and then to the nearest tenth, 12.1 seconds. Right, so I'll show you one more time. So we go second, trace, intercept, and just make sure your little like blinker, spider, cursor is close to the intercept you want it to be at, and then enter, enter, enter. Okay, so let's look at example number 2. So example number 2 says, last season, a struggling hockey club had only 7,200 season ticket holders. Yeah, Phoenix. The owner of the hockey club decided to raise the price of the tickets for the new season to make more revenue, so to make more profit. The existing cost of the package was $1,400. So that's what it cost originally. And then, so they analyzed it. They hired a market research company, and the company said that for every $25 that you increase the price, 100 less people will buy the tickets. So that makes sense to us, right? If you increase the price, less people are going to want to pay that. And then so they say they want us to come up with 2 different equations. One that figures out the cost, and one with the potential number of ticket holders. So let's do cost first. So what is the original cost of these tickets? Can someone put up their hand and let me know? Sam? Exactly. Okay, and are they looking to increase or decrease the cost of the tickets? Someone with a hand. Kevin? Increase, right? By how much? Yeah, so we're going to go 1,400 plus 25. That's for $25 increase. Yeah, so that's a good question because we know it's going to go up for every $25, which means it's going to go up in increments, right? So like 25, 50, 75, 100. 150. So that's why our X will go here because it's for every time that they increase it by $25. Okay? So we've figured out one expression. And then they say the potential number of season ticket holders. So we'll say number for that. So can someone put up their hand and let me know initially how many people bought tickets? Justin. You got it? And as they increase the price, are the ticket holders going to increase or decrease? Yeah, you got it. They're going to decrease. By how much, Justin? For every 25, so 100x, right? Okay, so these are our two equations. So here they say use your equations to generate an expression which represents the revenue obtained. So if we were just going to say, for the initial case where cost is 1,400 and number is 7,200, how would we use these to figure out how much they actually made? If I said, even before we look at this stuff, so if we're just looking at the last year, we say, okay, we sold 7,200 tickets, and they each cost, or each package of tickets cost $1,400. How much money did we make? You just multiply them, right? Like the cost times how many you sold. So to figure it out for this, you do the same thing. So we'll go profit equals cost times number. And we'll go 1,400 plus 25x, 7,200 minus 100x. Okay? So, okay. We're not too worried about it, so. Okay, so if we were doing this algebraically, we would have to FOIL this out, and we'd find that it was, I'll write it out, but it's 1,008,0000 plus 40,000 x minus 2,500 x squared. So if we were doing this algebraically, this is what we would need. But since we're doing it graphically, and we know that this and this are the same thing, we don't have to FOIL it. We can just put that into our calculators. So we can make y1 is equal to 1,400 plus 25x and 7,000. Yeah, this is a plus. Yeah, so you get this by foiling it, right? So you go like that, and that, and that, and that. Okay. So, but like I said, because we're doing this graphically, we don't necessarily have to FOIL it. We can just use this, which is, you know, I think we're more likely to make a mistake putting it into our calculator if we use that. So the one thing to remember if you do this is that you have to have these brackets in. Yep, go for it. Okay, so you guys can silently put them in your calculators. Like that. Yep, minus 100x at the end. Okay, so you can see that I don't see anything here yet. So I'm going to go zoom, fit. And so for my personal preferences, I like to see where my other x-intercept is. And I'd like a better view of my maximum as well. So I'll make my x max equal to 100. And I'll change this to 11 million.